The first of our numerical analysis problems that I want to look at is a very simple looking one. It'll come back to haunt us at the very end of the course, though. Suppose that you have a function f that's continuous on some interval from a to b, which you'll remember, informally speaking, means that there's no breaks in the graph, no vertical asymptotes or anything like that, although there could be sharp corners on the graph. Assuming that there is such a thing, I want to find an x so that f of x equals 0. I'll just call this the f of x equals 0 problem from now on. The simplest of all possible situations is when the function value f of a and the function value f of b have opposite signs. Since f is continuous, and I have to be able to draw the entire graph without picking my pen up, if the function is negative there and positive there, then somewhere between a and b, there has to be at least one place where the function value is 0. This is an informal statement of the intermediate value theorem from Calculus 1. That's not to say that there is only one such place. If the curve oscillates, if the graph of the function oscillates, it's entirely possible that there could be several places within the interval from a to b where f of x is 0. Our immediate goal right now is to just find one such thing. For purposes of concreteness, I'm going to assume that my function is negative at the left end of the interval and positive at the other end. The same kind of reasoning will work if it's the other way around. What we'll do is we'll take the middle of the interval. It's possible that the function value at m is actually 0. It's conceivable that we could have landed right on an answer of our problem. For now, I'm going to disregard that possibility. If I'm not sitting right at an answer, then f of m is not 0, meaning it has to be either positive or negative. So what we'll do is we'll look at the sign of f of m. If f of m is negative, then in this particular situation, I don't necessarily know that there's an answer to my problem between x equal a and x equal m because the function values have the same sign. On the other hand, if I do this middle thing, and it turns out that the function value of f at the middle is positive, then by exactly the same kind of reasoning, I know that there's a solution to my problem between what I'm calling a and what I'm calling m at the moment. What I'll do then is disregard the right half of the interval, and what I used to call m is going to be what I now call b. Whichever way it goes, though, I've cut the interval in half. I'm still calling the ends a and b, but they're only half as far apart as they used to be. So already starting to think about how we can organize these thoughts given a nice initial bracket that contains a solution. I'll let m be the midpoint. If the function value at the left end and the function value at the midpoint have opposite signs, if that happens, I'm going to set b equal to m, which means I have a smaller bracket. Otherwise, it must be the other half that I should throw away. I'll move the left end of the interval to this m number, and in either case, I end up with an interval that's only half as big as the first one was. As an example of this sort of thing, let's think about the function f of x equals x squared minus 7, and we'll start with the interval where a is 1 and b is 4. If I want to be paranoid about things, I'll make sure that that actually is a suitable bracket for what we're going to be doing. When x is 1, the function value, 1 squared minus 7, negative 6, is negative. When x is 4, 4 squared minus 7 is 16 minus 7, which is positive. So the function does actually have different signs at the different ends of the interval. I'll illustrate that situation by actually drawing the interval. I'll have x equal 1 at one end, x equal 4, and all that matters to me about the f, really, is if it's positive or negative. So I'll symbolize that by saying f less than 0 or f bigger than 0, as the case may be. To do the first step of bisection, I have to find the middle. If I average 1 and 4, I get 2.5. That's my midpoint. The deciding factor is going to be whether or not the function value at m is positive or if it's negative. I was lazy and used my calculator. It turns out that the function value at the middle is negative 0.75. The function value at x equal 1 and x equal 2.5 have the same sign. That means that doesn't tell me anything. On the other hand, the function value at the middle is negative. The function value at x equal 4 is positive. There must be a solution to my problem somewhere between 2.5 and 4. I'm going to disregard the left hand of the interval. I'm going to disregard the left end of the interval, and 2.5 is going to be what I'm calling a from now on. I'm going to draw the new interval on my paper the same size as I drew the original one. There's no sense in drawing tiny little things and trying to make sense out of them. To proceed, I'm going to find the middle of this new interval of numbers. The average of 2.5 and 4 works out to be 3.25, and the function value there is positive. This time, the function value in the middle is positive, so is the function at the right end. I don't know that there's a solution in there. On the other hand, f is negative there and positive there. Someplace between x equals 2.5 and x equals 3.25, there is a solution to my problem. My new interval is going to start there and end there. Comparing the first and second steps, it should be clear that it's not the case that you always throw away the left end or you always throw away the right end, even if your function, like the one we have, is monotone increasing. It depends on the details. If I want to do another step of bisection, I'll have my interval from x equals 2.5 to x equals 4. Well, crap. If I want to do, well, crap. I can recover from this without too much trouble. If I want to do another step of bisection, then I just continue this procedure. I'm going to find the average of 2.5 and 3.25. I'm going to find the midpoint of the interval. the average works out to be 2.8. The average works out to be 2.875. I need to know the function value that goes with that. Putting this on my calculator, it turns out that f at x equal 2.875 is 1.26 some odd. I don't really care much about the exact digits. All I care about is if it's positive or negative. If I wanted to continue, I'd find the average of 2.5 and 2.875, figure out if the function value at that spot is positive or negative, and then do the appropriate thing. The key point to observe here is I started off with some initial interval. After doing one step of bisection, this interval is only half as big as the original. This interval is only half as big as the previous one, so 1/4 as big as the original. This one would be 1/8 as big as the original, and so on and so forth. The left end and right end of these intervals are going to converge as the number of steps tends to infinity. Of course, in practice, you'll only do this until the left and right end are sufficiently close together. For obvious reasons, this is called the method of bisection. Bisection, in a certain sense, is safe. If you start off with a good bracket, and of course, if there were no rounding errors or anything, then bisection is guaranteed to work. We're going to look at another method called Newton's method, which is not guaranteed to work, but when it does work, it works very well. I'm going to think of having some initial estimate of the solution. I'll call it x1 here. There's a point on the graph to go with it. And also, from Calculus 1, we know how to get slopes of tangent lines. Those are the values of the derivative. I'll call the place where the tangent line cuts across the x-axis x2. The idea is, if I'm not too far away from the solution when I have value x1, and the graph of the function is reasonably nice, the function being differentiable, in the sense I can always get derivatives, if everything goes my way, then x2 should be closer to the real solution than x1 was. So I want to think about the tangent line. I want to think about where it cuts across the x-axis. I'll call that x2. I can think of this as doing some procedure to x number 1 to get x number 2. Once I've got x number 2, if I want to do this again, I'll do that same procedure, except I won't do it to x1, I'll do it to x2 to obtain x3, and so on and so on and so on. To talk about straight lines, I need to know two things. I need to know a point on the line, and I need to know the slope of the tangent line. And neither of those issues are any problem for us. A point on the line is x1 f of x1. The slope is f prime at x1. I can put this into the point slope form of the equation for a straight line. I'm interested in knowing on that straight line, when is y equal to 0? We're calling the x that makes that happen x number 2, so writing down that thought, I just get the following equation. There is an obvious danger here. If f prime at x1 was 0, then I'm not going to be able to solve that equation for x2 because I would have to do division by 0 in order to do so. For the moment, I'm going to pretend that that is absolutely not an issue. So what I'm going to call a step of Newton's method is this. If I have some estimate for the solution, which on the piece of paper I'm calling x1, here's what I do to get the next estimate. I take the estimate I already have and I subtract a fraction away from it. The fraction upstairs has the function value at my current estimate, and on the bottom I have the derivative of f evaluated at the current estimate. As I mentioned, if I decide that I want to do this again, if x2 isn't a satisfactory approximation, I can carry out this exact same sequence of operations and get what is hopefully a better approximation. I want to look at a little example using hand calculators again of this kind of thing. When we did bisection on this, the first midpoint that we calculated was 2.5. So in an effort to be fair in comparing these two methods, I'm going to start Newton's method at 2.5 and see what happens. If I feed x1 through the Newton method step in order to get x2, what I end up with is x2 equals 2.65. I'm doing all my calculations on a TI-84. X number 3 will be obtained by feeding 2.65 through this same procedure. If I look at the function value at x4, the calculator returns 1.17 e minus 11, which everybody knows is 1.17 times 10 to the negative 11 power. For most purposes, since that's 0 point and then 10 zeros, a 1, 1, and a 7, this probably is sufficiently close to being 0 that we should declare victory. In the last part of this video, I want to show how to code up Newton's method in a very simple, primitive way, and then we'll make it slightly less primitive, and that will be all for this one. So I've got my Windows system, sort of, and I'm going to open up a couple of PowerShells. In an effort to stay organized, I'm going to create a new folder that I'm going to put all my numerical analysis stuff in. Folder means the same as directory from the bad old days, so I'm going to make a directory called 4670. If I look and see what kind of files I have around, I have the files from the other day, and also I now have a new folder. I have 4670. It's empty right now, of course. Now, Within 4670, I'm going to have a wide variety of different things that I'm thinking about as we go along. I'll make up folders for them too, since this is just describing how to do stuff in an introductory way. I think I'll call my new folder Intro. So within 4670, I can see that there's another folder, another directory called Intro. It's empty as well. Now, the way that I'm going to work my environment here, I want both of these windows to be looking at this same location. So I'm going to Alt-Tab over to my other PowerShell window. I'm going to change directory into 4670. I'm going to change directory into Intro. So both of these instances of PowerShell are looking at the same location in the computer. One of these windows I'll edit, the other one I'll compile and run. It doesn't matter which one I do, so for right now, to get started, I'm going to redo Hello World and then put our new and interesting. I have the uninspired title of try1.f90 for the name of my source file. I'm going to save this out to a file, Control-O. I am not, though, going to exit my editor. I'm going to Alt-Tab over to my other window. And you can see that try1.f90 is sitting right there in the directory. So let's see if we can compile it. The compiler didn't complain about anything. There's my executable, a.exe, and then just like before, Hello World. The Hello World program is working. We are now going to mess with it. I'm going to Alt-Tab back over to my other window, and I'm going to put some stuff in my program. Firstly, I'm going to have a loop that I want to do in a minute. I have to have a loop iterator. It's best to use integers for this. So I'm going to declare some variable, I'll call it I, to be an integer. Strictly speaking, you don't need those two colons, but put them in anyway because, well, we'll see that later. I'm going to have an integer named I. The easiest way to do a loop is this. Do, then the name of the iterator equals the starting value of the iterator, ending value of the iterator. Depending on what languages you're already familiar with, there may be a slightly surprising feature to this. Also, Fortran doesn't care about indenting, but humans do because it makes it easier to read. So I'm going to be printing out stuff within the body of a loop. To indicate that in my source code, I'll just indent it some. I'm going to print two things. I'm going to print the value of I and also hello world. If this works, then what should be printed out should be 1 hello world, 2 hello world, and so on and so forth. I have to tell it where the loop ends. We do that with end do. If I've not made any typos or anything, then this should be all right. I'm going to save it, Control O, jump back to my other window, recompile it, rerun it. 1 hello world, 2 hello world, all the way out to and including 10 hello world. So in a fortran loop, when you say do I equals a number, comma, another number, the extreme values, in this case 1 and 10, are actually executed. We may need to keep this in mind if we decide to compare against some other languages. In the meantime, though, it's not very useful to just have a program that prints hello world out 10 times. Back to the source code. There is a thing that we will talk about in detail at another time, but for right now, you should just regard this as a thing that you should do at the start of your program. The reason for that is kind of monstrous, so we won't bother talking about it right now. I want to have some other variables. I want to have a variable that I'm going to call x, another variable that I'm going to call f, and another variable that I'm going to call f prime. Again, the 2 colons are not strictly required, but put them in anyway. I'm going to set x equal to 2.3. In my loop, I'm going to go in and take out hello world because I'm not really interested in that. Instead, I'm going to do this. For each x value that I've initialized to 2.3, I'm going to calculate some stuff. I'm going to calculate a number called f. F is going to be x squared minus 7. We raise a number to a power in Fortran by star star. F prime is 2 times x. You'll recognize this as being the function that we were previously talking about and its derivative value. That's how we do a step of Newton's method. I am overwriting the value that was previously in x with the new thing. I'm going to print something out to the screen, and then I'll go around in my loop and do the next iteration. I'll print out the loop index and the current estimate of the solution. After this line gets executed, this is the mark that tells it where the end of the loop is. If I is still less than 10, it will go back around, calculate f at this new x value, calculate f prime at the new x value, do the Newton step, print stuff out, and go around again. I'll save this. jump over to the other window, recompile, run it. And as you can see, I've got indexes 1 through 10, and the numbers involved end up looking like 2.64575,124, which is a pretty good approximation to square root of 7. A particular point of interest, though, is that it didn't take very long at all to obtain that value. By the time I was 3, you've already got your answer. That's interesting, and we're going to have to look into why it is that it's doing that. But for right now, we've talked about bisection, we've talked about Newton, we've talked about how to work simple problems by hand with a calculator, and now we've talked about a very simple way of doing this with a fortran program. I hope this is clear enough for everybody to easily understand. I hope you have a good day, and I'll talk to you again soon.